we've looked at orbitals, right? So I've explained in detail to you that orbitals are in fact mathematical functions called wave functions, right? You can write a wave function for everything, right? So this is a wave function for one electron in a box, right? We square the wave function, we get a probability distribution function, okay? Psi squared is what I'm calling an orbital. We do the same thing. We take the same approach and we apply it to an atomic system. We get different types of orbitals, which you'll have to memorize, right? We have the s orbital, the p orbital, and the d orbital. There are 5 d orbitals, right? 1, 2, 3, 4, 5. There's 3 p orbitals, pxy, px, and pz, right? Px, py, and pz. So 3 p orbitals and s orbital, okay? Now, let's try to find a way to make all of this really simple. There's a special type of notation, we call that quantum numbers. We can utilize quantum numbers to specify what orbital we're talking about, right? So by solving rigorously the Schrodinger equation over here, we solve the Schrodinger equation. We can obtain, from solving the Schrodinger equation, four numbers, which we call quantum numbers, okay? All right, so let's see over here, right? So the first quantum number is called the principal quantum number n, right? This tells you the size of the orbital, right? So if n can be 1, 2, 3, 4, 5, any integer value, right? That'll indicate the size of the orbital, okay? The next quantum number is the angular momentum quantum number, right? This will tell you the shape of the orbital, right? So, for example, n can be 1, 2, 3, 4, 5, just whole numbers. The angular momentum quantum number will tell you the shape of the orbital, and it is basically n minus 1. So if I say n is equal to 1, then L is equal to 1 minus 1, which is equal to 0. Okay, this is the angular momentum quantum number, okay? This is what we call the subshells, okay? So the principal quantum number is what we call the shell, and then the angular momentum quantum number, we call that the subshell, okay? The magnetic quantum number can be any number from negative L to L. This will tell you the orientation of the orbital in 3-dimensional space. So, for example, if n is equal to 1, L is equal to 0, then m is equal to 0, which means, right, my orbital, right, no matter how I orient this orbital in 3-dimensional space, it's the same orbital, right? So if I take an s orbital, spherical mathematical function, I rotate it in 3-dimensional space, I still have an s orbital. Okay, so for principal quantum number 1, L is equal to 0, m is equal to 0, I am talking about the s orbital. This is the s orbital, okay? But what if n is equal to 2? If n is equal to 2, then L is what? L is equal to 1, because L is n minus 1, right? Which means L will range from 0 to n minus 1, so L can equal to either 0 or either 1, okay? Which means if L is equal to 0, that is directly the s orbital, right? But if L is equal to 1, then I told you earlier that L ranges from negative L to L, then I can have negative 1, 0, and 1, right? So there's 3 orbitals orientated in 3-dimensional space, which means what orbital am I talking about here? I'm talking about the p orbital. You have the py, px, and pz orbital, right? So for a quantum number, angular momentum quantum number L is equal to 1, I get the p orbital. And m will tell me the orientation of my p orbitals in 3-dimensional space, negative 1, 0, and 1. So in summary, these numbers will tell you what orbital I'm talking about. So solving the Schrodinger equation, I get numbers which we call quantum numbers, right? So if you think about the principal quantum number n, you're talking about, if you go back over here, right, for example, n is equal to 3, this number 3 contains all of the orbitals, right? So I have the L is equal to 0, 1, and 2, right? I have the s orbital, I have the p orbital, and I have the d orbital, right? So these quantum numbers are convenient because they tell you exactly what mathematical wave function I'm talking about. Okay, so I've summarized this over here, right? So principal quantum number 1, L is 1 minus 1, 0. You have 1 orientation. This is the s orbital. For principal quantum number 2, I have 2 subshells. I have the 0 and the 1, meaning I have the s orbital. I got three orientations over here, so this is the p orbital. For principal quantum number n is equal to 3, I have 0, 1, and 2, meaning I have the s orbital, the p orbital. Here I have 1 orbital, 2 orbital, 3 orbital, 4 orbital, 5 orbital. I have 5 orbitals, which means this is going to be quantum number, this is going to be the d orbital, right? So you got the SPD shell. So if I take these orbitals and I arrange them in an energy diagram, so something similar to what I've shown you earlier for a particle in a box, right? So you can solve rigorously using the time-independent Schrodinger equation. You get the final functional form of the wave function for an electron in a one-dimensional box. I can calculate using Schrodinger's equation, right? H psi is equal to E psi. I get the energy value. I can plot the energy value along the y-axis. This is the energy axis, right? That's the energy axis. Right? I can get the values along the energy axis. Okay. So if I were to plot this up, right, I get n is equal to 1, just like the particle in a box. N is equal to 2, n is equal to 3. So for quantum number n is equal to 3, it contains all of these orbitals. 3s, 3p, 3d, all of these orbitals, meaning I have the L is equal to 0, L is equal to 1, and L is equal to 2. Okay, so you can see that these little boxes over here, they indicate 1 orbital, meaning you got 5 orbitals in L is equal to 2. They're all degenerate. The word degenerate means they have the same energy, right? So no matter which d orbital I pick, right, dyz has the same energy as dxz, has the same energy as dxy, has the same energy for this one and this one. They all have the same energy. That's why we write them as boxes grouped together, right? They have the same energy. Same thing for the p orbitals. pxy, px, px, py, and pz are all degenerate p orbitals. Okay, so that's how we typically do this. Okay. All right. So let's do some problems here. Okay. So go ahead and work on this problem. Okay. Tell me what values of the angular momentum and magnetic quantum numbers are allowed for the principal quantum number n is equal to 3. Okay. And also answer the question, how many orbitals exist for n is equal to 3. So go ahead and pause the video and work on this problem. All right, so hopefully you had some time to work on this problem. Okay, so here are the solutions. N is equal to 3, right? So I told you earlier, L is what? L is n minus 1, right? So that's 3 minus 1. It's 2. So L ranges from 0 to 2, right? So 0, 1, and 2. We have the s orbital. That's 1 orbital. The p orbital. That's 3 orbital. And the d orbital. That's 5 orbitals. So we have a total of 9 orbitals. So hopefully you found that quite easy. Okay, that should be quite straightforward. All right, let's work on the next problem. Right, so go ahead and spend some time and work on this problem. Give the name the magnetic quantum number and the number of orbitals for each sublevel with the given quantum numbers. Okay, so here I give you, I state for you, n is equal to 3, L is equal to 2. Now tell me the name of the orbital, right, and the number of orbitals for each sublevel. So go ahead and pause the video and work on this. All right, so hopefully you had some time to work on that. All right, so for the first one, right, n is equal to 3, but within shell n is equal to 3, we have a lot of subshells, right? It could be 0, it could be 1, it could be 2. But in this case, I give you L is equal to 2. Meaning, I now have what? -2, -1, 0, 1, 2. That is 5 orbitals. Meaning I'm talking about the d orbital. The d orbital from what shell? From what shell? Well, look at n. N is equal to 3, so the d orbital is the 3d orbital. You have a total of 5 orbitals, right? Same thing over here. N is equal to 2, meaning what? Meaning I have 0 and 1. But I tell you over here that L is equal to 0, which means I'm talking about the s orbital, right? The s orbital from what shell? From 2. So you got the 2s orbital over here. That is exactly 1 orbital, right? N is equal to 5. L is equal to 1. I have the 5p orbital. That's 3 orbitals, right? N is equal to 4. L is equal to 3, meaning I have the f orbitals. So we have the s block, the p block, the d block, and the f block elements. Okay, so we're talking about the f orbital. Right, so that's a total of 7 orbitals. Okay. All right. All right, so solving rigorously for the Schrodinger equation, I told you earlier that we get out 4 quantum numbers, but I've told you 3. I've told you n, l, and m. But there's actually another quantum number which is equally as important. That is the spin quantum number. Right? So electrons can have spin, which means they can precess along an axis. Right? They have a spin. This could be spin up or, spin down. And this was first observed in the Stern-Gerlach experiment. Here, a beam of hydrogen atoms are put through a small pinhole through an asymmetric magnetic field. What happens is when the precessing of the spin interacts with the magnetic field, the beam of hydrogen atoms split into 2, and you have a plus 1/2 spin and a minus 1/2 spin, as shown over here. Okay. This is indicated, right, as plus 1/2 or minus 1/2. We would indicate a plus 1/2 spin as an arrow and a half arrow, right? This is plus 1/2. Make sure to write the arrow with only half, right? You don't want a full head. Half an arrow indicates half spin. And then in the opposite direction, you have the minus 1/2 spin. Meaning what? We can go back to this diagram over here, right? So, for example, I have 1 electron in the 2s orbital with a positive 1/2 spin. All I do is I write that in the energy diagram. All right, so if I told you I have 1 electron in the 2s orbital with a minus 1/2 spin, then all you do is you write that in the opposite direction. Okay? So Pauli, he said that no 2 electrons in the same atoms can have the same quantum number. So for exactly 1 electron in an atomic structure, you will only have 1 equation describing that electron in your atomic structure. So 1 electron in an s orbital will have a wave function which will always be different from another electron in the same s orbital, meaning one will have a half spin, the other will have a negative 1/2 spin. So the Schrodinger equation, the wave function of your electron in a particular atomic structure will be unique per that particular electron, right? So a plus 1/2 spin in a 2px orbital will always have a different equation from a negative 1/2 spin in the 2px orbital, right? This is the idea of Pauli's exclusion principle, right? let's look at energy splitting. Okay, so the one on the on the top here, this is the helium spectrum, and the bottom here, I've shown you earlier, this is the hydrogen spectrum. We can see that we only get so many emission lines for the hydrogen spectrum. This is due to electronic transitions, which I've shown you earlier, right? So I have this energy diagram, E1, E2, E3. So you go up, you relax, you release a photon, okay? Because helium is a 2-electron system, right? You have, when you rigorously solve for the energy levels, right, you get more energy levels. And in some cases, you even see a splitting between the emission lines. And this is due to a phenomenon which we call electron-electron repulsion. Okay, so as your atomic structure becomes more complicated, the energy levels become more complicated. And the interaction of the energy levels with energy itself, right? So applying an energy to an atomic system to induce emission, right? The artifacts we're getting in terms of the emission lines will also be more convoluted, right? As the equation we're solving, right? So we're not solving the Schrodinger equation for a particle in a one-dimensional box. We're solving the Schrodinger equation for a potential well, which is now your nuclear attraction with particles consisting of multiple electrons. So the energy levels will also reflect the complexity of that problem, okay? Let's look at another important concept, okay? So this is the nuclear charge on your electron in your atomic structure. For example, if I have a hydrogen atom and exactly one electron, right? So this positively charged 1+ charge will attract the electron towards the center, right? However, if I were to increase that charge, in the case of helium plus over here, this is a 2+ charge, the pull, the attractive potential on that electron is significantly more, 2-folds more. Okay, so this is more difficult to remove. Meaning, if I wanted to pull this electron out of my atomic structure, this is easier to pull relative to this structure over here. Okay, so let's look at another effect called shielding. Okay, so in this effect over here, let's say I have 2 electrons in helium, right? These 2 electrons will feel the pull of the 2 protons at the center of my helium atom, right? So that's quite typical. However, if I were to look at a different atomic structure, which is more complicated, with more shells to say, for example, lithium, right? You got 3+ in the middle, but here you have a full 1s shell, meaning I have a positive 1/2 spin and a negative 1/2 spin, right? So the 1s orbital shell is completely full. So remember from now on, whenever you have a full orbital shell, your atomic structure is stable, right? Every atomic structure wants to reach a full shell. Full shell is equal to is proportional to stability, right? So the more full the orbital shell, the more stable that orbital is. So here I have a 1s orbital shell which is completely full, right? Why? Because, right, if you go back over here, see, this is exactly 1 block for the 1s, 1 block for the 2s, 1 block for the 3s, meaning each s orbital can only hold 2 electrons, right? These 2 electrons have different mathematical functions. One wave function for the +1/2, another wave function for the -1/2. Okay? So over here, this shell is stable, meaning this electron in the 2s orbital, remember the 2s orbital can hold up to 2 electrons, but here I only have 1 electron. Okay? So this electron will feel the nuclear charge at the center to a lesser extent because the electrons in the 1s orbital acts to screen the charge from the 2s orbital, right? So this is called shielding, which means this electron will be more easier to remove than this electron, right? So this electron over here, right, will be more difficult to remove because it's pulling the full force of the nuclear charge pulling on it relative to an electron which is experiencing shielding from the inner core orbitals. Okay, so another concept I'd like to introduce is called the penetration effect. So in the penetration effect, here we have the 1s, the 2p, and the 2s orbital, right? We can see over here that the 2s orbital over here actually penetrates closer to the nucleus of my atomic structure. Meaning what? Meaning if I were to arrange these energy levels along the energy axis, what happens is you will begin to fill, right, the shells over here first, the 2s first before you fill the 2p orbital. This is called the penetration effect. The ordering of the orbitals along the energy axis depends on how close the radial distribution function penetrates closer to the nucleus. Okay, so you'll see this a little bit more in detail when we look at electron configuration. Okay. All right, let's continue on with building electron configuration. So elements in the periodic table can be divided into several blocks. So here I have the S block elements, the P block elements, the D block elements, and the F block elements. So these are the S orbital, the P orbital, the D orbitals, and the F orbitals. Right? So these orbitals are part of subshells. So for example, n is equal to 1, we have only the 1s orbital. N is equal to 2, we have not only the subshell for the 1s orbital, which is a lower energy level, we have the 2s orbital and the 2p orbital, or we also call those subshells. So how do we fill up these orbitals? So Aufbau states that the electrons are filled in the atomic orbitals from the ground state, meaning that you fill the electrons from a low energy level to another high energy level, right? So for example, if I have n is equal to 1, then we have 1s orbital. If n is equal to 2, then we have the 2s orbital and the 2p orbital. Right? So I told you before that electrons have spin. It could be spin up or spin down. So Aufbau states that you're going to be filling these orbitals from low energy level to high energy level with the spins paired up initially. Then you come back and pair the spin, and then you move up to the 2s orbital, right? And then the next electron will completely fill that orbital shell. And then the 2p orbital, you want to fill the upspin first, followed by the downspin. Right? So pretty simple. So let's begin with the simplest two elements. So hydrogen, if you look at the periodic table, hydrogen big Z, or the proton number, is equal to 1. For helium, big Z, the proton number, is equal to 2. The proton number is also known as the atomic number. You can see this number over here. That's a 1, and that's a 2. Right? So this is Z, or the atomic number. Okay? So if Z is equal to 1, which means if I have one proton in a neutral hydrogen atom, right? It's in some neutral hydrogen atom, then I have exactly one electron, right? Because if you look at the classical picture of the atomic structure, one proton, you'll have one electron, because you got to balance the charges. Helium, you have two protons, which means you have two electrons. So now we have to find a way to put these electrons in the electron configuration. And there's two ways. Right? So the first way is the NL number notation. Right? So N is the principal quantum number, L is the angular momentum quantum number, and the number over here, that indicates the number of electrons. So this one over here, hydrogen has one electron, right? you go to the periodic table, it's in period 1. So this means n is equal to 1. Right? So the period number indicates the principal quantum number. N is equal to 2, n is equal to 3, 4, 5, 6, 7. So this is already conveniently arranged for you in the periodic table. Okay, so this over here, principal quantum number for hydrogen is 1. Right, L is equal to 0. This means this is an s orbital. It's got 1 electron, so 1s1. This is the electron configuration notation over here, right? For helium, right, this will be, you have the principal quantum number 1, your subshell is s, and you have 2 electrons, so here you have a 2, okay? So pretty simple. You can then fill this up in a diagram which we call an orbital diagram. So an orbital diagram is written left to right from low energy to high energy. So if you come over here, right? So you want to write 1s, 2s, and 2p. Okay, so you want to write it in one line. So the orbital diagram will keep going, and you'll see that more clearly when we begin to do the examples. Okay, so I prefer half arrows. So to be conventionally correct, you have to draw the half arrows. So 1s, 1 electron, you put in 1 electron. So each s orbital can take 2 electrons. So this over here, 1s2, 1 electron spin up plus 1/2, 1 electron spin down minus 1/2. Okay? So if you were to draw the energy diagram, you would have drawn something like this. Right? So you begin with 1s, and then 1s, and then 2s, and then 2p, because these are in the same shell, we put them along the same energy axis. Okay? But in terms of the orbital diagram, all you'll do is you'll just list the orbitals from low energy to high energy from left to right, with the energy axis being along the x-axis. So that's pretty simple. Right? So lithium has big Z. Z is equal to 3, which means I have to find a way to put my 3 electrons in this orbital diagram. So first electron, second electron, third electron. Right? So Hund's rule, it states that every orbital in the sublevel is singly occupied before any orbital is doubly occupied. Meaning, you want to put the upspin first in each orbital. So each one of this is one orbital, right? So 2p, you got the 2px, 2py, 2pz. You got the 3p orbitals. So if I were to fill up the p orbital, then I would put each half spin first, and then followed by another negative 1/2 spin. So pause the video and spend a few minutes to write the orbital diagram and the electron configuration for each of the following. Okay, so pause the video. All right, so hopefully you had some time to work on this problem over here. So we'll pick a few just to show you as a proof of concept. So we know that oxygen has a big Z of 8, right? So which means we have to arrange 8 electrons in the orbital configuration for oxygen. So first thing, so 1s plus 1/2 minus 1/2 plus 1/2 minus 1/2. Okay, now this is really important. You want to put the upspin first, then followed by the downspin. Okay, so look at this carefully. There are no tricks over here. This is quite simple, right? Just look at big Z and then put the electrons in the orbital diagram. So quite simple. Okay. A few, something to notice is you want to make sure that when you fill the orbital diagram, the spins, right? So you want to put spin up and then spin down. So please remember that. Okay. Right. So same thing over here. So this is from sodium all the way to argon. This is called a noble gas. You can see that the noble gas configuration, especially if you look at the periodic table, this column over here, these are noble gases, and it's been conveniently used to abbreviate the electron configuration. For example, when you're looking at something like n is equal to 4, n is equal to 5, you really don't want to write, 1s2, 2s2, 2p6. You want to abbreviate that. And you can do that by taking the most recent noble gas as your starting point. So for example, if you come to lithium over here, this is 1s2, 2s1, I can technically write this as, I know lithium is here, right? So before lithium is helium, I can technically write this configuration as helium followed by 2s1, and this is the electron configuration for lithium, right? That's helium. So you can take the most recent noble gas in the period before your element and then use that to abbreviate the electron configuration. Okay, so this is a bit helpful, right? So, sometimes we want to be able to quickly arrange the orbitals from low energy to high energy. And one trick is to write down 1 to 7, 2 to 7, and then in the middle put 3 to 6, and then 4 to 5. And then label this as your S shell, your P shell, your D shell, and your F shell, meaning you will begin to fill the orbitals in the following order. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, right? So it'll follow that particular order, okay? So one thing to note is that we actually fill the principal quantum number 4 for the 4s shell before the 3d shell, right? And this is due to the fact that if you look at the radial distribution function for the s orbital actually penetrates closer to the nucleus relative to the d orbital, right? So it's more easier for electrons to populate the s orbital. So we fill the 4s orbital first before we fill the 3d orbital. So I've shown you this diagram before. So you got the s block elements, the p block elements, the d block elements, and the f block elements, indicating s subshell, p subshell, d subshell, and f subshell. Right? So I will not give you this table. You have to know this. You have to be able to look at the periodic table and know right away what subshells you're dealing with in your particular electron configuration. Some elements fill differently, and if you look over here, you can actually see that sometimes it actually prefers to have a half-filled shell, right? So you think of it as 2 steps, right? The first step is you want to achieve the most stable electron configuration, which is essentially a full orbital. But sometimes in a lot of systems, to achieve a half-filled orbital is actually quite stable, right? So in some cases, you will end up promoting an electron in a lower orbital shell to a higher orbital shell to achieve a half-filled state, right? So you'll see this again when you look at your quiz, okay? Right, so I've mentioned a bit of this before. You want to be able to group the electrons into different categories, right? So you can use the inner core electrons by dictating the most recent noble gas configuration, right? So for example, if I look at potassium, I can actually go argon, right? Potassium's over here, right? I can go argon. The period number indicates the principal quantum number, right? So this is n is equal to 4. So argon 4s, you got 1 electron in potassium. So that's a convenient way of utilizing the periodic table, right? So the period number will tell you the principal quantum number. You can utilize the atomic number to get the number of total electrons. You can actually abbreviate the electron configuration by writing. Additionally, I'd like to introduce to you how to utilize the periodic table to look at different properties of each element, okay? So the periodic table, I'd like to formally introduce to you the periodic table. In the periodic table, we can divide the elements into 3 classes. metals, nonmetals, and metalloids. The metals are highlighted in blue, the nonmetals are highlighted in yellow, and the metalloids are highlighted in green over here. Okay? So, a few trends that's important to you. One is the ionization energy, right? What does this mean? It means the energy required to remove an electron from an atom. If I remove an electron from an atom, then I calculate the energy required to remove that electron. We call that the ionization energy. This applies to all elements. Okay, so you've seen before, we talked about the photoelectric effect and the work function. So they are sort of the same thing, but they're quite different. Okay, so the ionization energy applies to all elements. Okay, but the work function is a property intrinsic to some orbital energy level, that energy gap, typically in metals. Okay, the electronegativity, this indicates the affinity. It sort of indicates how willing an electron, how willing an atom is how likely an atom is willing to accept an electron. We call that the electronegativity. The electronegativity increases from left to right, bottom to top across the periodic table. So in this manner, it'll go up along the diagonal of the periodic table. Okay. In the same way, the ionization energy will also go up left to right, bottom to top across the diagonal of the periodic table. Okay. On the other hand, the atomic radius, right? The atomic radius will increase from top to bottom, right? From right to left and top to bottom down the diagonal of the periodic table. This indicates the atomic radius, right? The electron affinity, right, will also go bottom to top, left to right, across the diagonal of the periodic table, as seen over here. The electron affinity indicates the energy release when you add an electron to an atomic structure. That's the electron affinity energy. The atomic radius is typically related to the number of orbitals, right? So the more orbitals you have, the further and further apart you're spreading out that mathematical wave function, and you sort of have a larger atomic radius as a result of having a lot of orbitals, right? And electronegativity, I've explained that to you. And a lot of stuff can affect electronegativity. This can range from things like orbital stability. Some elements are really, really close to being stable. A single electron will actually stabilize the outer orbital shell. We call that we call the outermost orbital shell the valence shell of an atom. Okay. So let's look at the ionization energy. It is the amount of energy required to remove an electron from an atom. Okay. So if we look over here, right, so we have a lot of these trends, right? So hydrogen, helium, and then we drop down, right? And this can be due to many effects. For example, shielding can also affect the ionization energy of certain elements. And as you've seen before in the example I've explained to you, right? So it's a non-monotonic trend, meaning you go up and then you sort of come back down, you go back up, and then you come back down, right? So a lot of reasons can be, you can attribute this nonlinear trend to a lot of reasons, which I'm not going to go over all of them. But we'll look at one example, right? So try to answer this in your head. Why is the ionization energy of helium higher than calcium? If you look at helium over here, helium has a full orbital shell, right? So this is what? This is the 1s2. It's a really, really stable shell. And when things are stable, I told you before, it's difficult to remove an electron from a stable orbital. But if you look at calcium, right? Look at the periodic table. Calcium is here. N is equal to 4. So if we use the abbreviated electron configuration, it's AR, K, and Ca, meaning, right? AR, right? K and Ca, and it's equal to 4. So what is it? It's 4s, right? 4s what? Calcium is 1s, 4s2, right? Because the atomic number here is what? It's 20. So you fill all the shells up, and then you have 4s2, okay? Meaning, in the outermost orbital layer, you got what? You got a full s orbital. One here, and one here, right? It's more difficult to pull electrons from a completely filled valence shell, right? Especially those with a smaller atomic radius relative to something like calcium. Calcium has 2 electrons in the valence shell, so the ionization energy of that is much lower, right? So this is the completely full valence shell, and the atomic radius is smaller. Okay, so this, you also do have 2 electrons in the valence shell, but the ionization is much lower because the atomic radius of calcium is also much larger. So we always talk about the nuclear charge, right? The charge, the attractive potential pulling on the electrons in the outermost orbital, right? So we feel that nuclear charge to a smaller extent. The electronegativity is the tendency for an atom to attract a shared pair of electrons towards itself. In general, this is in general, not always the case, because a lot of these orbitals can interact in different ways, and you might see some exceptions, right? En, or electronegativity, increases from left to right across a periodic table and decreases from top to bottom down a periodic group, meaning the electronegativity increases left along the diagonal, left to right along the diagonal of the periodic table. So our most electronegative element is fluorine. Okay? So if I were to ask you, why is fluorine more electronegative than iodine? You look at the periodic table, right? So fluorine is over here. Iodine is down over here. So what happens? So as you go down a group, the number of orbital shells go up, which in effect shields the magnitude of how the shared electrons in the valence shell feels that nuclear attraction, right? So we can also say this in terms of the increasing atomic radius. Okay, so as you can see here, iodine, right? So the atomic radius, the periodic trend, it goes up, down along the diagonal of the periodic table, meaning the atomic radius for iodine is larger than the atomic radius of fluorine, right? So that all that means is that that's why fluorine is more electronegative. Okay. So hopefully that's quite clear to you. Right. So this is the atomic radius. Okay. It goes up, down the diagonal of the periodic table. Okay. And that's just a measure of the nucleus to the outermost valence shell boundary, right? To that outermost mathematical wave function, which we call the valence shell boundary. Okay. Electron affinity energy. It's the energy change which occurs when you add a single electron to a gaseous atom. That's it. By convention, that's all it is. And all of these numbers are computationally tabulated for you. So you can look up these numbers in tables.